Here we will look at planes and also points and lines that intersect or in those planes. A plane is a flat surface that extends forever in all directions, 2 dimensions. Now we're going to look at how many different ways we can orient a plane through a point. So I just have one point. I drew it right there, point A. So I could say the plane is just this flat surface that's already there. So I'm going to simulate the plane with this pink sheet. So that's going through that point A. Remember, it has no sides at all, so that makes it kind of weird. Now, I could also have my plane go like this through point A. Imagine it going through the paper to the other side. It could even be tilted and rotating all the way around. I can rotate it this way. And not only that, I can turn and angle it. It can be straight up. It can be rotated. So there are many different ways I could have a plane going through that point. In fact, there are an infinite number of ways. Now we're going to look at Now I added a second point. So how many different planes can I have go through 2 points? So remember, my plane must intersect all of these. So I could have my plane actually be like the flat surface that's going through, that has both those points. See, they're both in this plane. Or I could have my points be like that, and I can rotate this and tilt this around, almost like I'm turning it around a line. And so there's still many different ways. I can't turn the plane this way anymore because I have to go through both points. But even so, I have many options on how much I turn it around that. So my plane can be anything that rotates around this, which actually, believe it or not, makes it an infinite number of planes. Finally, I added a third point, point C, and I want to have a plane that goes through all 3. Well, if I was doing this like before, remember, I'm not really supposed to bend my plane. This is not a plane. It has to be flat. And so if I do this, I can go through A and B, or maybe I could move it and go through A and C. The problem is, to do it through A, B, and C, the only way I can get this plane to go through all 3 is if it's flat. So when you have any 3 points, it doesn't, unless, and we'll talk about that in a second, any 3 non-collinear points, then you can do only one plane through those. Now the interesting thing is, let's say I added a third point D, and I'm going to use this to help me out. If a fourth point D, I can't count. If my point's in line with my other 2 points, meaning it's collinear, then I'm back to the 2-point situation where I can have an infinite number of planes going through the 2 points. But if my points are not collinear, where they don't share a line, there's only one plane that goes through all 3 points. And here's a possible illustration you could do for showing that the plane is through 3 non-collinear points, and you could use the previous illustration from the line for the 2 points if those points are collinear, making a line. So when it comes to naming planes, as we said, any 3 points, you notice how we had to come down and stay flat with all 3. So that's why we use 3 letters to name it. So we use capitalized script. We can also use a capitalized script letter, so like this letter here. So I could call this clear plane here, this kind of flat one, plane ABD, or I could also call it plane V. Those are the same plane. Now another name for the plane is EFC or BEF, and there are actually quite a few more, so I'll let you try to name some more, as long as the 3 points are not collinear. So, for some more individual practice, give some other names for this plane. Now, another example is, can you use the points A, E, B to determine a plane? No, because they're collinear, and remember there are an infinite number of planes that can go through that line. And for your individual practice, how could you name, and I should say, the shaded plane? Cross that out. Pointer options. The shaded plane, not the unshaded plane. Your notes are right. The PowerPoint's wrong. So how could you name the shaded plane since we've been naming the unshaded plane? Axioms and postulates are something else we want to start talking about. An axiom is something which is accepted as true, and it does not need to be proven. So something that you might consider an axiom is 1 + 1 is 2. I don't have to prove it to you. You accept it as fact. Postulate is just another word for axiom. Some basic axioms of Euclidean geometry. Well, through any 2 points, there's exactly one line. Therefore, any 2 points are collinear. So the axiom is through any 2 points, there's exactly one line. I went ahead and extended it to say, well, then that means any 2 points are on the same line. Through any 3 non-collinear points, there's exactly one plane, like we saw in the video earlier. Therefore, any 3 points are coplanar. We're going to look at the postulate that if 2 points lie in a plane, then the line that contains those points lies in the plane. Now, here are my 2 points, and I could just kind of draw a line through it, but I thought I'd go ahead and get a little more concrete. So I have this coffee stirrer that is modeling my line. It's technically a segment. And so you can see through any 2 points, if the 2 points are in the sheet of paper, in this case trying to mimic my plane, then the line really wants to stay down in the plane. It doesn't want to leave the plane. So this postulate is true. For any 2 points in the plane, the line that contains those points is also in the plane. Okay, we're looking at the example where 2 flat walls meet in the corner of a classroom. So which postulate best describes this situation? Well, the first choice here is through any 3 non-collinear points, there's exactly one plane. Well, we're really talking about 2 different planes here. So I wouldn't say that one doesn't really strike me as the one that we're talking about. We're talking about 2 planes meeting. Okay, if 2 points lie in a plane, then the line containing them lies in the plane. Well, we're not really talking about 2 points. We're talking about 2 planes. All right. If 2 lines intersect, then they intersect in exactly 1 point. Well, that's true. In fact, all of these are true. But is that really talking about the 2 planes that we have here in the wall? And choice D, if 2 planes intersect, then they intersect in exactly 1 line. So here's a plane, there's a plane, pretend those are the walls in the classroom. And if you look at that intersection where they meet, it is a line. Now, admittedly, here, a line segment. But the idea is since planes go on forever, it would be a line.